Right, yeah, it's recording. Well, today you may notice we skipped quite some chapters. Now we jump to chapter 14, which is the chi-square test. Well, I kind of want to go this flow, like we first introduced the hypothesis testing. Now we get this chi-square test, which is kind of like very similar to what we talked about last week, but we are just testing a different format of your data. And once we get into the material, you probably will get why we talk about this first. But anyway, let's proceed to the chi-square test. So I said this is a new test. You noticed it's called a chi-square test. So what it is used for? Okay, and we have been talking about like the situations and different things follow a certain distribution, like normal distribution, binomial distribution. But what if you are looking at a set of observations? Like you have your data, but how can you know like what distribution it follows? And if you want to check, or you can just watch, just eyeball the observations and guess if it's whichever distribution. You might say it's close to some distribution, but how close is close? That's what we do for doing hypothesis testing. Like we have some assumption and we want to test it out. Secondly, what if you want to look at the relationship between people's political parties and their opinion on some specific policy? So it's basically categorical. It's no longer continuous data. So in this case, we in the hypothesis testing that we covered seems not relevant to this situation. So that's why we're going to learn about this chi-square test to deal with these two different scenarios.
So now it's more how do you say, qualitative data?
Yes, right, exactly. Yeah, we'll look at the qualitative data with chi-square test. So for the first bullet, we'll get example here. See, everyone has one of four blood types. So that's true, we know. Suppose we believe that 45% of the people are O, 35% are A, and 15% are B, and 5% are AB. So this is our belief, and we want to test it out, and this is our null hypothesis. And if we collect a sample with 100 people, with this is our observation, like 47, we observed 47 of them have O type blood type, and 32 have A, and 15 have B, and 6 of them have AB blood type. And this is our data, and so we just want to compare how close our sample to the expected value if our belief like this here about this proportion is true. So we want to compare how close this sample is to the expected value under the condition that the null hypothesis is true. So clearly this is a hypothesis testing, right? The test statistic would be based on like how different the number of observations in the categories, like these four categories, from the expected numbers when H null, the null hypothesis is true. And for this case, we would use chi-square test. And I have listed a fun fact about blood type and also the donating link for you if you're interested. And so basically for this situation, we want to test whether our data from the observation fits a particular distribution or not. So we saw the data like from different categories. And if we do a multinomial experiment, so this is more generalized example or the situation we're dealing with. We're doing a multinomial experiment. We have multiple categories from 1 to k. So from the previous blood type example, k equal to 4, right? And in general, we use this pi as a probability that a trial results in category I. So we have 1 to k categories, and we use p1, p2, up to pk to denote the probabilities that the result would be in category I.
The previous example, it was like 145, 135.
Right, exactly. And we use this pi star to indicate the value of pi claimed by the null hypothesis. So the value that we claimed in the null hypothesis, we will denote it as the pi star. It's just like previously when we do the hypothesis testing, like we have mu equal to mu 0. So this pi star is playing the role of that mu 0. So if we have n trials, then the expected count in each category would be this total number of trials times the probability that we believe from our null hypothesis that the trial results would be in category I. So this is the expected count if it's under our null hypothesis. So basically this pi is, pi is what you observe, and pi star is the value that you declared in your null hypothesis. And we know how to get the observed, like this is basically our data, like n1, n2, up to nk, where this, comparing to the previous example, this n are just the like this 47, 32. So this is our n1, n2, n3, and n4. And we also need to calculate the expected observations, expected count in each of the category by use this n times pi star. So pi star is from your null hypothesis. What do you believe? So this is clearly listed. How do you get the observed value and the expected value? Remember, we collected 100 data points, and we have this percentage here. We need to get the expected count, so we just do the multiplication here, and we need these two things. And we mentioned we would have to calculate. We compare these two, this observed and expected. We want to compare like how close they are. If they are close enough, we would say, okay, it follows the distribution that we declared. But if it's far, we will just reject the null hypothesis. So when this H null is true, pi would equal to, sorry, I forgot to change the denote here. Pi equal to pi star. It's not pi 0. Yeah. And we expected that each ni will be close to n times pi star. I will correct this on the uploaded slides. Yeah, so
it's always a star, not the O anymore.
Well, in this case, I use star because like when I equal to 1, it's kind of easy to like you get p1 0. You cannot distinguish the p1 0 with p10. Yeah. So yeah, I changed from previous, but I forgot this page. So we expect that several of the observed counts will really differ from the expected counts if the true value of pi differ a lot from the null hypothesis estimates pi star. So we're comparing these two by looking at their squared deviations. So we're taking their difference and take the square of it, and then we sum them up to see how far they are from zero. So if the sum of the deviation close to zero, we know like this two things, the expected and observed are close, right? Again, we have the question about how far from zero is too far. Yeah, so in this case, we would need do a hypothesis testing, and we would need some distribution in order to carry out this hypothesis testing. So formally, let's see, the null hypothesis and alternative hypothesis are like this. So this is P1 equal to P1 star, PK equal to PK star. That's the null hypothesis, what we believed about the proportions. Where the opposite of this is just at least the one PI does not equal to PI star. So this is like they are all equal, and the opposite would be at least one of them do not equal. And our test statistics is like this. So we mentioned that we use the observed minus the expected, take their difference and square, and divide it by the expected cons, and we sum them over all the cells. Oops. All cells means we have 4 cells here, so we would sum them. Yeah, take the sum of these 4 categories. So that's what it means, all cells here. And formally, we will say I from 1 to n and sum over this quantity. And we have a condition here. If n times pi star greater than 5, then our test statistic, this thing, is approximately follows a chi-square distribution with k minus 1 degree freedom. So now we know the test statistic would have a distribution. It's just a chi-square distribution. We didn't talk about this chi-square distribution, but we'll just talk about it here. Yeah, to follow the flow of the hypothesis testing, we would need to get a p-value. But in this particular case, the p-value is the value under the curve to the right of your test statistic. So it would always be your right tail probability. And if like this condition, is not met, you will just combine some of the categories to make it satisfy this condition. So yeah, have to take care of this in order to use this chi-square test.
Why is 5? Like if it's greater than 5, you got the distribution. If it's less.
Yeah, like I said this here, if this condition met, this test statistic approximately follow a chi-square distribution. So well, this 5, I mean, it would be like determined like more of a rule of thumb. So that is, well, I guess the larger the better. So I mean, if it's not 5, if it's greater than 5, like 10 or something, but yeah, and then you will be more close to a chi-square distribution. But normally when people collect data, well, collecting data mostly like cost time, money, so people might just have very limited number of samples. But this is kind of the probably like a relatively small number, easy to satisfy for most of experiments. So I guess it's like a balance of like your time and money, and also like how good your theory is, like in terms of this testing. Well, this is the oh yeah, I'm about to talk about the chi-square distribution. Well, so it's just a distribution, like continuous distribution. It also got its like PDF, just like on this plot. And for different degree of freedoms, you will have different curve shape. And as you can tell, it's non-symmetric. And when the degree of freedom increase, like for this one, when the degree of freedom equal to 15, it's almost gets symmetric. But in general, it's a non-symmetric and always positive random variable if it follows chi-square distribution. And remember the degree of freedom is k minus 1, where this k is the number of categories you have. And the curve, yeah, I said it's non-symmetric. Oh, it's skewed to the right because it got a longer right tail, heavier right tail. Skewed to the right, always greater or equal to 0. Well, some fact about this distribution is that the mean would always be the degree of freedom, and the standard deviation of the random variable, if it follows a chi-square, it would be the square root of 2 times your degree of freedom. So this is just some fact for the chi-square distribution, and this is what it looks like. Yeah, let's just look at this example. This is how we do the calculation. So first of all, you would have to get the corresponding, well, observed data is the data given to you, like the data we collected, and the expected, you would have to do the calculation on your own, like n times pi star, like for each of these cells. You calculate this, and then you do your test statistic and sum them over up. Well, this is explicitly telling you how to do this calculation. And we get a value of chi-square being 0.546. And we know, well, this k equal to 4, and the degree of freedom is k minus 1, which is 3. So this thing would be from a chi-square distribution with 3 degree of freedom. And this is how we do the p-value. So it's always on the right tail. So it's the probability of chi-square greater than. So it's greater than, then it's the right tail. Greater than this test the statistical value, and this is how you do it in R. And we can tell this p-value is pretty large, so we will not be able to reject the null hypothesis. So yeah, so that our belief about the distribution, like the proportions for different blood type, we would say, yeah, this we would support that claim. Okay, and whoops. Yeah, I don't think. Let me see if my R lab would have. Oh, sorry, I'm supposed to start this earlier. I don't remember, but I don't think I have that. Well, yeah, the example I have is does not include the blood type. But anyway, all the oh, why is get back to the start? So all the details are already here. Let's do slideshow. Okay, let's take a look at a different example from the book. So if you think back of your biology class, you might remember this experiment. It's a very famous experiment. So if you cross a plant with, like this is, I think it's called gene, or yeah, the gene
I don't know what word it is.
sequence or something. Yeah, let's see if the gene would be big A, big B, and big B, with another with small a, small b, and small b. And you will get this, these plants, like big A, small a, big B, small b plants. And crossing this, like big, small, A and B, and it says the expected for photon type with probability P1 being this, P2, P3, and P4. So this is what we believe about the probabilities for each of the 4 category, and that's our null hypothesis. And if we do the expected cell count, like we would have to fill up like those cells by n times the pi star, like those are our like p1 star, p2 star, and we just, we need to calculate the expected counts for each of the cell. So this is how you do the calculation, like how you get those numbers here. N equal to 16, 11. And this is the observed value given to you. This is the data given to you. We will do this example in R. So, well, we have this data given to you, and we calculated the expected counts on our own by this. And let's go to our, well, maybe it's easier. We'll just take a look at of the, So this is the, like I need this R markdown file, and that's what it generated. So let's just directly look at here. Like this HTML file and also this R markdown, where it has all the code here, will be all Blackboard, and you also can see the code here actually. So we know the observed data, and we calculated the expected by use n times pi star. And next, we will calculate our test statistic, which is the sum of this, like squared difference divided by the expected count. Well, this is like step by step. We take the difference and take the square of them, so we get 4. It will be doing the point-wise, element-wise square. So when you do this, and after the square, you divide it by the expected, where the expected is also a vector. So in this case, it will be correspondingly do a point-wise, like it will use this value divided by like this corresponding the first element in this vector. So this is how you get this. And then you just sum them up, like take the sum of these 4 numbers. So like this is telling you how I get it. And just to be noticed, I will do this element wise. So, and this is your test statistic. And now let's do the p-value. So the p-value would always be the probability of this chi-square greater than, so the right tail probability greater than this test statistic. And you do this 1 minus, because it's on the right. So you do the 1 minus p chi-square. So this is how you get the CDF. The CDF for this chi-square distribution, where you have to supply this test statistic and also your degree freedom, k minus 1. So where here we have 4 categories, k equal to 4. So the degree freedom is 3. well, this is how you get the p-value. Or you can also do this, like the p chi-square, and you tell R that lower tail is false. That means it will take the upper tail. Upper tail means the right-hand side, the tail on the right. Yeah, so you can also do this. You will get the same value of for p. Okay, so this is for this example. Well, you will see homework that will do very similar things, where you have to calculate the expected counts on your own, and also like do this test the statistic and find the p-value, and then make the decision if this p-value is less than, say we use the significance level 0.05. If this p-value is less than 0.05, you will reject your null hypothesis and in favor of the alternative. If it's greater than 0.05, you just you filter reject. Okay, let's get back to, well, yeah. So we can also use this chi-square test to for other scenarios, like to check the fit to specific distributions, even for continuous distribution. But let's consider example for to check if a random variable follows a binomial distribution. And let's say we have n equal to 4. Well, binomial distribution, if you still remember that, that is about you take like n trials and you count how many success out of these n trials. So that's what a binomial distribution is like. And we know like the probability of getting a success, we denote it as theta. Well, previously we used p, but just to be easier to distinguish from this proportion thing, we will just use theta instead of p for this binomial distribution. So, well, for n trials, we could get 0, 1, 2, 3, 4 success. So we have 5 different 5 cells. So we have cell 1 to 5 representing 0 to 4 successes. And so we are testing. Okay, go ahead. So we have this test statistic, similarly as before, P1 equal to P1 star. Well, we have to calculate the P1 star, P2 star, up to P5 star, according to this like binomial distribution PDF. Because we are claiming this is a binomial distribution, and we are saying we have, well, for this binomial distribution, we have parameter n equal to 4, and the probability of getting a success is 9/16. So in order to get this PI star, we would use this PDF for binomial distribution. So you get your P1 star up to P5 star. So once you get the PI star, and you can calculate the expected cell counts by like this n times PI star. Well, this is for like use the chi-square in a different scenario. And well, if we use that in continuous distribution, what we do? So for continuous distribution, we can just divide or chop up the sample space into k cells. So we know that continuous distribution, like the sample space is continuous, like either is from 0 to 1, from A to B, but we can divide them up into k different intervals, but they are like connecting them together, it will be the whole sample space. But once we get this k cells, we can calculate the observed and expected just as before, like counting how many of them follow in different of the intervals. And in this case, the probability for each cell would be like, well, just what it is, like the probability of this random variable fall in this cell, like from AI -1 to AI. This is the i's cell. So this is theoretically, how do you calculate the pi star? If you, well, because we said it's a continuous distribution, well, calculating this probability would actually being you take the integral over this PDF. Well, this is the hypothesis, the PDF of this x. So this would be the probability of x following this range. So yeah, this is the, I think this is just theoretically we do for continuous distribution. And let's see an example for that. But this is for uniform distribution, which is simpler. Let's see, we want to see if the onset of labor is distributed evenly through a 24-hour period. So we divided the day into k period of length 24 divided by k. But here, let's say we use k equal to 24. So basically we divided the whole day into like 1 hour interval. And the null hypothesis is saying it's uniform distributed, like the number of labors. So this fx is the uniform distribution on this interval from 0 to 24, and which would give us like uniform distribution. We know it would be like all equal probability following each of the cells. So the pi star would be 1 over k, 1 over 24 when we have 24 intervals. And say our data in total have this many data points, this many labors, and we have the observed for each hour, how many labors we have in each hour. And for this case, the expected would just be the total n times your pi star, because like for all I, for each hour, we have equal probability of getting a labor, because we said it's a uniform distribution. So that's why like all intervals should have the same probability. So for all this, for each hour, the expected would be the same value like this, 49.416. And yeah, now you get your observed and the expected, and we can get back to R and say how are we going to do this one. So we have a vector for this observed, like in this 24 hours, how many labors we have in each hour, and or expected, and do the same thing, or you get the test statistic by same formula, and we know k equal to 24, degree of freedom k minus 1. So yeah, do not get confused with the t distribution where your degree of freedom is n minus 1. In this case, you would have an n, you also have a k, but remember to use k minus 1 for this chi-square distribution. So in this case, we're using this syntax like to get our p-value by specifying the lower tail being false, meaning we are taking the upper tail. Okay, so this is another example for continuous distribution. How do we use the chi-square test to test the fit to a continuous distribution? Well, we've been working with the frequencies along one variable or one row. Now let's move to a two-way table where we have like two variables. where we put them on a table. That's why like we call it two-way table, where one variable on the rows and another variable on the columns. So basically you will see something like this. Like on the rows, you have like different categories for one variable, where we have I categories for the first variable. And for the second variable, we have J categories, and we put them as this, and we call this as a two-way table.
You see this at the beginning, like one of the first classes, we have like blood type and like groups or something, and you can see like probabilities of each box.
Well, for that, like for the blood type example, we actually have only like one row, right? We have A, B, O, and AB. And we have the corresponding counts like N1, N2, N3, and N4, but here, where that's only, oops, that's only like this much. But now we're extending it by adding the rows. Previously, we have like 4 columns, right?
Yeah.
And now we are adding like another variable. Let's see the race of people. We can
Like
put.
I said, we see this like one of the first chapters.
Oh yes, actually we in the probability. Yes, that's like I think in the second chapter when we work on those probabilities. Yeah, it's kind of related. You will see how did we use the like small little things that we learned previously. Because we will mention like independence, like how do we consider how do we test for independence? Where when we're working on the probability chapter, we all know like what it means by independence of 2 events. Okay, so that's a two-way table, and yeah, we are working on 2 variables now. And actually, we have 2 different situations for testing with that two-way table. Say we have, so this is the first situation. We have I populations of interest and 1 for each row. And each population is divided into the same J categories. So the populations on the rows and the categories on the column. So we're interested in this case, we're interested in whether the proportions between categories are the same for each population on the rows. Example would be 3 department. We have like 3 department store chains, and that's our that's the populations of interest. And on the row, on the column is the proportion of payments in like American Express, Visa, MasterCard, or cash. And this type of test, like when we try to test whether the proportions between the category are the same for each population on the row, we call it the test for homogeneity. So this is one type of test. An example would be like we have this 3 product line, like 1, 2, 3. This is our 3 populations we're interested, and we have the number of like non-conformity, I think, product for different reasons, and we have the count for each of them, and we want to compare the proportion for each of this category. Are they the same among these 3 population? So this is a test for homogeneity. So let's take a look how do we do that formally. Now we have I populations, J categories, like here, 3 populations, 5 categories. So a sample of Ni individuals is taken from the I's population. Like this is N1, N2, N3 for 3 population, and total N is this one. like on the corner, is the sum of these three. So n is the sum of ni, and we use this nij to indicate each of the cells. So I is for the populations and j is for the categories. And we use this n dot j. We use this to denote the sum. We sum over I. So n dot j, see, n dot 1. So j equal to 1. So this is your j equal to 1, j equal to 2, 3, 4, 5. And so if we sum up over i's, we got this being our n dot 1, n dot 2. So this row is our n dot j. Similarly, this is our, like, well, we use ni, but we can also see it ni dot because we are summing over the j. So let's define this Pij is a proportion of individuals in population I would fall in category J. So basically we need to translate this count into the probability thing, into this P proportion. So now we have the counts and we need to get it into P proportions. Okay. And so for this test of homogeneity, we have this null hypothesis being the proportions of categories for J categories are the same for all populations. So the proportions are the same for all populations. That is saying for every for every J, this is J. The font is, it's funny. So for every J, we know this P1. So this 1, 2, up to I, this is our I populations. And we know this proportion are always the same for each of the categories. Yeah, homogeneity is defined as the quantity, the quality, or the state of being all the same. So in this case, how do we find our expected cell counts? We will use this E expected. We use a hat because we will get it from the data, or from kind of estimated proportion. So we estimate this uniform Pj common to all I populations. So this is what it says, like all of this equal to, say, Pj. And this is done with Pj hat being n dot j divided by the total number n. So that is the proportion of total over all populations that are in category J. So this is how we get the Pj, and we can take that with our ni to estimate what proportion of the sample I will be in category J. I know this sounds very confusing, but actually when you look at the table, I feel like the table is make more sense. And when you have the table, you have corresponding like ni's and nj's and the total n and each of the corresponding nij, and you can get them to Pij.
So the null hypothesis gives for every column the same proportion or probability for any population, any row, right?
Right.
Okay.
Well, maybe it's easier to say here, like the null hypothesis is that we're assuming all this, yeah, they are all the same. Yeah, the proportion are all the same across your across the populations. Yeah, across populations. Yeah. And we will, oh yeah, I think we skipped here. So this is how do we get the expected counts for IJ's cell? So we use this Ni. Actually, you can consider it Ni times Nj divided by N. So this is how you get, well, I told you this, well, do I have this? No. This Ni, well, this is your N1, N2, N3, Ni's. And this is your Nj's. J equal to 1, 2, 3, 4, 5. And that's like, for this one, you will just use this times this divided by that.
Yeah, the N is 375. Right?
Yeah, the total N. Yeah. So this is the formula how you translate that count into, yeah, that's your observed, you get to the expected. Yeah, so once we get that, we just do the same thing, but now we are summing up more cells. Now we have a whole table. Instead of previously we only have one row of data, we sum them up. Now we have a whole table. You have I columns, I rows and J columns, you sum them up all together. So you see that you take the sum over I and over J. And now what is the degree freedom? We still have this chi-square and we need to determine this degree freedom, which is I minus 1 times J minus 1. So once we get the distribution for your test statistic, we get back to the route of the hypothesis testing. We do the p-value just the same as before. Like you just do p chi-square and specify lower tail being false. Get you the area and the curve to the right. Again, if p-value less than alpha, you reject the null hypothesis, which you in favor of the alternative. Well, so I said we have two different situations for when we work with a two-way table. And the second situation would be we have a single population of interest. And each individual is categorized into two different factors. So we have two factors. The first factor on the rows, we have I categories for the first factor, and then we have J categories for the second factor. So again, it's still a two-way table. And in this case, we're interested in whether the two categories are independent of each other or not. So the two factors, if they are independent or not. Example would be each purchase is classified. So we're interested in looking at the purchase, classified by which department the purchase was made and in what method of payment. So the two factor, department and method of payment. The population, one population, we're looking at the purchase. So for this type of test is test for independence. Yep, let's look at an example here. Well, testing independence in Star Trek. The Star Trek fatalities. Yeah, fatalities by their like uniform colors. So we have two factors, fatalities, whether it's dead or alive, and we have different uniform colors, blue, gold, and red. So two factors make a two-way table for us. And we're testing whether there is a connection between the color of the uniform and the fertility rate. So we're testing whether this factor is independent of this factor. And we have the data listed here. We will work on this a bit later. So this is just telling you like the scenario we want to test for independence. Let's get back to the denotes. The notations. The notations. Again, we have I categories for one factor, J categories for the second, and a total of N individuals. So that total n would always be like in this lower right corner. It equals the sum of this 2 and also the sum of this 3. And we use this Nij to, so it's similar as before, like N11, N12, like we have this Nij denotes each of the cells. And we also use N dot J and Ni dot to denote, like this is N1 dot, so this is for I equal to 1, and this is I equal to 2. So this is N2 dot, and this corresponding to this 3 corresponding to N dot J, J equal to 1, 2, 3. Now, yeah, once we have this Nij, we can get, like, translate them to Pij and Pi and Pj by you just divided them by the total number, you get the corresponding Pij, corresponding proportions, I mean. Yeah, this is just telling you what it like physically mean. This Pi dot is that a randomly individual for in category I, so category I for factor 1. And this, when we're talking about J, would be the random individual for in category J for factor 2. I feel it's easier just to look at like those quantities. Well, anyway, how do we do this test for independence? Well, I mentioned this. So this null hypothesis now is that the individual's category with respect to factor 1 is independent of their category with respect to factor 2. So this is just what we have learned. If A and B, so event A being that individual following whichever category in factor 1, and event B being that for factor 2 in whichever category. So this intersection of these two events is corresponding to, like, for this one, it would be have a uniform color being blue, and it's a dead event. So the intersection of these two events, and yeah, this intersection probability of this intersection equal to the multiplication of the probability of each individual event, would means that these two are independent. And translated back to our scenario, that means for every pair I and J, and we have this Pij equal to this Pi times Pj. So this is equivalent. And how do we find the expected cell count, E? Remember, if we want to do this chi-square test, we would have to get the expected counts comparing to the observed counts. So now, assume our null hypothesis is true, we calculate the expected counts for each cells. So similarly as previously, we just do you can also do things like Ni times Nj divided by N, or you can also do this N times Pi and Pj. And I feel like this is easier if you look at the table. Well, yeah, I think everything is the same from previously, like for the test of homogeneity, in terms of calculation, it will be the same, but we are testing different things. I mean, like our null hypothesis and alternative hypothesis would be totally different from the test for homogeneity. So this is the null hypothesis when we test for independence. So Pij equal to Pi times Pj for all I and J's. whereas opposite would be they are not equal for some I and j. If we have one not equal, that means they are not all equal, right? So same test statistic and sum up over all cells and same degree freedom. Oh, I think I forgot to mention, we have to make sure we have this expected value, expected counts for all the cells would be greater or equal to 5. This is just to ensure that our test statistic would follow this chi-square distribution. Like if this test statistic not follow chi-square distribution, that means our test is not reliable. So we cannot basically use this chi-square curve to do to get our p-value. So this is something to be noticed. Well, we mentioned if this is not satisfied, we can always combine some of the cells, right? Again, for p-value, they're the same way for the calculation. Yeah, just want to let you know that pay attention, like for a test of independence and test for homogeneity, their hypotheses are totally different, even though like the scenario behind this two-way table, they are totally different. But the chi-square test would always be the same, like chi-square test, but we're just testing different hypotheses. Well, I think I have this example this example in R that we can take a look how we do that in R. Oh, we're supposed to look at it here so it's clearer. Okay. Well, this is, I'm supposed to run, let's just do it for this two different type of test. So this is the example corresponding to the test for homogeneity. So I just put the data here. Well, this example 14.13 is corresponding to this data, and we'll work on it in R. So I just put this matrix, basically this matrix, this 3x5 matrix, like all of this in R, by I make a matrix like this. I put all the numbers and gave it the number of rows. I have 3 rows, so it will give me well, why I always get back to R. Well, anyway, that's just in case you are not familiar with this. So I have the data. So I just basically want to show you what the data looks like. So I just put the data into a matrix of 3x5. And I also gave it the row sums and column sums directly, where you can also like do the sum in R. And total N, those numbers I just got from the slides, right? From here. Okay. Well, remember we want to get this test statistics. So how do we get this EIJ hat? So this is what we want to calculate. We want to get, and eventually sum up over all these values, the square the difference divided by this expected counts. So well, you should, there are many ways of doing this, like do the calculation with that matrix, but this is just one way of calculating. So I did a loop. So I first define this sum being 0, and then I will update the sum in the loop. So I goes over like from 1 to 3, and J goes over from 1 to 5. And for that means for each I and J, I will calculate the EIJ, which is like NI times NJ divided by N. And each this piece is calculated as here. So this data IJ would get you the NIJ, and it will like you do the minus, take the square, and divide it by EIJ. So I calculate each individual and sum them up one by one. So this is what it's doing in this double loop. And this summation of these things would give us the test statistic. And then we need our degree of freedom being capital I minus 1 times capital J minus 1. So this is our degree of freedom, and this is how you get your p-value from your chi-square distribution. And we see this p-value is really small. Well, for most alpha, like alpha being 0.05, 0.01, this p-value would be smaller than that. So we reject the null hypothesis of homogeneity. So we're in favor of the alternative. That means the distribution is somehow different from our 3 subject group for this 3 production lines. Okay, so this is your test of homogeneity. And for this Star Trek fertilities, well, I just did the same thing, get the data into a matrix. Oops, sorry. You need to come back here. So yeah, I get this data, like all these NIJs into this matrix. And this is I manually calculated. Like this is taking the sum over rows. So 1 means the rows of this matrix, and 2 means taking the sum over the columns of this matrix. So this will give you the row sums and column sums, where you can also copy, just copy from here, like row sums, column sums. And N would be the total of your NIJs. So this is to show you what they are. And again, test statistic would be the same way for calculation, but let's just like formally write the code for it. So that means you do not hard code the capital I and capital J, where you just count by this n row and n column. Basically, you can use this set of code once you define those correctly. Define the data correctly, and everything should just pop out for your test statistic if you use this set of code. And the degree of freedom is this I minus 1 times J minus 1, and degree of freedom being 2, and we get our p-value. Well, this p-value less than 0.05, so we conclude that they are not independent, which means we rejected the null hypothesis. And the conclusion is that they are not independent. Okay, so I think that concludes our lab and the material for the chi-square test. And the homework will be available the end of today. Yeah, I think I said it will appear like midnight of today. And slides and the lab code will be up on Blackboard. And yeah, I think that's it for today. Any questions, comments? If not, I will stop my recording.